So, yeah, our next speaker is Dr. Alex Byrley. He is actually also another UB alumni. He received his PhD from Buffalo, and his dissertation focused on logarithmic frequency waveforms. He currently is a signal processing scientist at Mastodon Design in Rochester, and he designs and implements machine learning and signal processing algorithms for radar receivers. He is also the new chairman of the Rochester IEEE Signal Processing Society and the new lead organizer of the 2021 West New York Image and Signal Processing Workshop. His research focuses on software-defined waveform detector and receiver design. So now let's welcome Alex. Alex, we cannot hear you. Did you turn on your mic? No, still, let me see. I cannot hear you. Let me check. There is still no sound.
I also don't hear any sound.
Yeah.
Though his mic is activated.
Okay, nope, how about now? Can you hear me now?
Great. Yeah.
Okay, yeah, I just had to close the app and come back on.
Okay.
Okay, so now everything should be fine.
Yeah, we can see you and we can hear you.
Okay, so you can see my window too?
Yes.
Hey, great. Okay, so welcome everybody. My name is Alex Byrley. I'm with Mastodon Design over in beautiful sunny Rochester, New York. And today I'm going to talk about logarithmic frequency waveforms and their applicability for beyond 5G communications. So I have a bunch of published work regarding this stuff. So it's not proprietary to Mastodon Design or classified or anything like this. Everything is in the public domain. So what are logarithmic frequency waveforms? So these waveforms are a new class of joint radar and communication waveforms that are built by mapping good radar codes onto the magnitudes and phases of a set of logarithmic frequencies. So I know on this slide, there's a lot of stuff. And if waveform design isn't your field, this might be a lot all at once. So what I'm going to do is just blurt it out, and then we're going to take a couple steps back and see if we can build up some knowledge to try and figure out everything that's on this slide. So for the waveform designers in our audience, the key idea behind these waveforms is that we're going to use the logarithm. Right? The logarithm converts a multiplicative Doppler shift into an additive shift. Okay, and that enables us to do what's called matched filtering over the logarithmic frequency spectrum. And by doing this, we can simultaneously detect a waveform and estimate its Doppler shift. So now if we choose the radar code to be what's called an extended Goulam ruler, we are going to enable Doppler invariant communications applications. So these waveforms, specifically extended logarithmic frequency rulers, they excel relative to other waveforms when the Doppler shift is large. So as promised, we're going to go back, review the Doppler shift, and then we're going to talk about types of these waveforms, and we're going to show how they might be used as a communications waveform, and talk about a little bit about their performance, and then we're going to wrap it up. That's it. So what is the Doppler shift? The Doppler shift is a dilation of a waveform due to relative receiver source motion. So let's see, let me get my pointer out here. So now let's imagine that we are in this plane here, and we're moving with some velocity vt to the left of the screen. So, and we have some transmitter over on the left, let's say it's in front of us, that's going to transmit us some information, right, with this green waveform. From our perspective, because we're moving towards the transmitter, what we're going to receive is this blue waveform, right? It's compressed in time due to the Doppler shift. So it looks like it has a higher frequency. On the flip side, if we were moving away from the transmitter, it's going to send us this green line again, and what we're going to get back is this red signal here. So it's expanded in time due to the Doppler shift, and it looks like it has a lower frequency. Of course, this is a problem, right? Because this signal we receive is not the signal that we were expecting. The frequencies have changed. And if we're using multiple frequencies at once, multiple carriers, this problem gets a lot worse, because this effect is multiplicative, as we can kind of see up here in this equation. So C of V is the signal is the frequency we receive, and C over here on the right-hand side is the frequency we send out. And we see there's some multiplicative change. So this means if your carrier value is different, each carrier gets shifted by a different amount. So the spectrum that we receive is not the spectrum at all that the transmitter sent out. Logarithmic frequency waveforms, well, they solve this problem by making finding the Doppler shifted frequencies easy, right? So from these waveforms' perspective, in the presence of Doppler, the logarithmically warped frequency spectrum looks the same as it would if there were no Doppler, right? As if this time compression thing didn't happen. Well, all that really happens is that the whole entire spectrum gets shifted to the left or to the right. But the relative change between our frequencies, well, they don't change. So basically, it's the same spectrum, just shifted. So this allows us to do a simple correlation for both detection and Doppler shift estimation. Correlation, of course, is called employing a matched filter. So here we have our Doppler shift estimate equation, if anybody's interested. So we see in this picture here, you can imagine the spectrum that we expect is this blue guy here, and what we receive is the orange guy here. Of course, it looks exactly the same. All that happens is it gets moved to the left. So basically, it's not a problem of what we received, it's a problem of where we received it. So here is a taxonomy of these waveforms. Today, we're only going to talk about this right-hand group over here that we call the logarithmic frequency rulers. So here's the first one, the multicarrier logarithmic frequency rulers. So we can see here the top picture is the code that we use to create this waveform. The middle picture here is what the power spectrum of this waveform looks like. You see, it looks just like the code that we built it from. The distances between the frequencies are basically the distances that we got from our code. The exact equation is over here on the left. The transmitted signal, the one we send out, is just we stack all these carriers on top of each other and send them at the same time. And it looks like this, right? We see that we have high peak to average power ratio for these types of waveforms, and this is, pretty common for all multi-carrier types of waveforms. So because we only really care about what the power spectrum looks like, it means that we can define the phases however we want. And by doing this, we can enable a communications waveform. So extended logarithmic frequency rulers are basically just the same thing as logarithmic frequency rulers, the multi-carrier version, except we have the ability now to pack more of these carriers within the same bandwidth. And it uses what's called an extended Coulomb ruler. You can see here the extended Coulomb ruler has lots and lots of sticks in it, and therefore our power spectrum has lots and lots of carriers. And here's what the transmitted signal looks like. You can see, again, high peak to average power ratio. But we can change the phase of the waveform. So hopping logarithmic frequency rulers. So the code and the power spectrum are mismatched, but you can get the idea. basically what we do is instead of placing all the carriers on top of each other, what we're going to do is space them sequentially in time. And again, we can define the phase of our carriers however we want, but by spacing it in time, we can also create different codes, right? Just like a frequency hopping code. So we can also use that to transmit information if we wish. So here's a receiver for these things as a communications waveform, what it might look like, for instance. So it comes in, we convert it to a digital format, and then we go to this top branch here. First, we compute the power spectrum, then we logarithmically warp the frequency, we do our matched filter, and we get our Doppler shift estimate. Then, what we can do is go back into the time domain on this middle branch here. We can save some of those carriers as pilot tones, for instance, if we want to estimate the channel or whatnot, and this will allow us to do a time domain matched filter because we know the phases. Once we do that, this gives us a very precise estimate of where the signal is in time. We can send this out to a communications receiver. Whatever phase modulation we used, that corresponds to this receiver over here. So, as a communications waveform, detection and carrier estimation are done incoherently, right, by match filtering the logarithmic frequency power spectrum. The carrier estimation, of course, is done by just finding where the peak in our logarithmic frequency spectrum is, as we showed before. So logarithmic frequency carriers are therefore free to be phase modulated without affecting the detection performance or the carrier frequency or Doppler shift estimation. Of course, like I said before, we can reserve some carriers to allow time domain match filtering, but we can also use amplitude modulation because it turns out any subset of a Goulomb ruler, which is the code we use to create these things, is also a Goulomb ruler. This modulation type will affect the detection probability, and there's some other details there that we won't go into today. So here's a little bit more of a technical slide. So on the left-hand side, this shows the detection resolution using our logarithmic frequency detection. We see that because we threw out the phase, we have a very broad range of detection. Right? This bottom axis is basically shows you where relative to the window under which you take your power spectrum, where the waveform is within that window. The 0 shows that it's right on top of that, and left and right means it's completely outside the window. You see that when you're on top, right directly in the middle, you get the best performance. So this other y-axis here shows basically how big of a shift it is relative to the original carrier. 0 means there is no shift, and -4 to 4 means you're 4 times as big as the bandwidth that you sent out. So you see that the peak is consistently. It doesn't really matter how big the Doppler shift is. But if we can estimate the Doppler shift, we can go back into the time domain and then do a matched filter. You see that if we do that, while the side lobes can be kind of high, the peak, the main lobe peak here is very thin. And that allows us to have a very precise estimate of where this thing is in time. So that removes a lot of the phase errors that we might encounter due to mismatch in time. Here's an example of what the hopping rulers look like. You see they have a much better ability to be localized in time, and that's because of their, they use time in the waveforms themselves. So here's an example of how these things work in Doppler. So on the top here, what we have is what's called the extended matched filter. Basically, that is how we estimate Doppler for a linear frequency chirp signal. So in the middle here, we have our logarithmic frequency code, and in the bottom here, we have our logarithmic frequency ruler. The size of these waveforms is 2 to the 16 samples, so it's a pretty big waveform. So therefore, it has really good signal-to-noise ratio performance. Right? Signal-to-noise ratio performance is directly related to how large the waveform is because we're taking a Fourier transform. So we see that while the linear frequency chirp is, a large Doppler shifts make it very difficult to estimate the actual Doppler. For our logarithmic frequency waveforms, that's not the case. They excel under large Doppler shifts. And again, these Doppler shifts are almost relativistic, so it shows how robust these things are to Doppler. So here's an example of what might happen if we encounter some multipath. So this is a automotive channel. So on the top, again, is the extended match filter. And then we have the ruler without what we call a multi-bandpass filter, and the bottom for what we do have a multi-bandpass filter. And then basically that's just a filter around the carriers that has to do with the maximum Doppler shift that we expect, which we can always generally design. So up here, NR is the number of reflections. Theta is the average power in those reflections relative to the direct path. And we see that while multipath really affects the extended match filter, even though it's pretty good, it doesn't so much for our guys. So the logarithmic frequency ruler, if we apply the multi-bandpass filter, has a very, very low percent Doppler area. And that's because basically we're getting rid of the noise by the multi-bandpass filter. And also our ability to estimate Doppler. We see that also multipath does affect the ability to estimate Doppler. We're not as good as if there was no multipath, but we're still pretty good. And that's because when multipath happens and all of these signals are being added together, we're throwing away the phase. We're just using the power. So in some cases, if, for instance, theta is high, right, it actually helps us estimate the Doppler because we get more power in. So in summary, logarithmic frequency waveforms are a new class of Doppler estimation-capable radar and communications waveforms. The second class, the rulers, are particularly suited for communication application use because we can do the detection and carrier estimation completely incoherent, which means we can use phase to transmit information. We can finally synchronize the waveform in time by time domain match filtering of pilot carriers after we do the detection and the estimation of the carrier and the Doppler shift. And we see carrier estimation is robust to large Doppler shifts in multipath. Their major drawback is, of course, the high peak to average power ratio, but that is like OFDM. This can be mitigated by spreading the waveform in time and creating these hopping rulers, or we can do a hybrid version where we send a couple carriers at a time and then some other later. Along with intelligently designing the message codebook, perhaps we can also play with the phase to bring down this peak to average power ratio. So in summary, logarithmic frequency rulers are a promising new waveform class for future 5G and 6G applications, especially when we want to communicate with moving targets, and especially when we want to communicate with moving targets that are moving quite fast. Here are some references, and that's it. Thank you very much. Now we'll stop for questions.
Thank you, Alex.